The approach taken in formulating and solving the equation of motion of the two-body problem that we've seen so far is not unique, and alternative formulations are not only possible, but in some circumstances preferable. There are some topics, like the derivation of Lagrange's equation and the discussion of the dynamics of resonance and resonant encounter, where a different mathematical approach is required. This is the Hamiltonian formulation, which we're going to see now. We formulated the equations of motion of the two-body problem, having two masses, m1 and m2, moving under their mutual gravitational attraction. And doing that, we derived the differential equation, r dot dot plus mu over r cubed times vector r is equal to 0, the solution of which is a conic section. Early on in the analysis, we chose the reference plane to be the orbit plane. However, this vector equation is equally applicable to motion in 3 dimensions, with the radius vector being x, y, and z, and the velocity being x dot, y dot, and z dot. We're going to use here the variables r and p being the momentum, using a slightly different notation. In terms of the unit vectors, I, j, and k in Cartesian coordinates, so we have the components rx, ry, and rz of the radius vector. And similarly, we can write the same for the momentum, where the momentum then has components px, py, and pz in each of the 3 directions. Now, r is the radius vector, the relative position vector from m1 to m2, and p is the linear momentum of the system. And as usual, v is r dot, the velocity. So we can now write the equations of motion in terms of the Hamiltonian equations. We're going to define what this quantity h is, but the operators grad p and grad r are vector differential operators that are given by is the gradient using p as a coordinate, and the same thing for the gradient in r, which is the usual. To write the equations of motion in this form, then we need to find the quantity h, which is the Hamiltonian. The Hamiltonian in this case is p squared over 2 mu star minus mu star over r, where, as previously, mu is g times m1 plus m2, but we have a new quantity here, which is mu star, which is a reduced mass. This quantity h here is the Hamiltonian of the two-body problem. So we replaced now the 3 coupled second-order differential equations, which are these ones, by an analogous system of 6 coupled first-order differential equations given by the Hamiltonian equations of motion. So let's use these definitions here to see how the equations of motion will be. Let's take first the derivative of h with respect to p. There is only p in the first term. So what we get then is r dot is equal to p over mu star. And for the momentum, you take the derivative of the Hamiltonian with respect to r, which occurs only in the second term. So you have p dot is equal to minus mu star over r squared in the radial direction. So r cubed times the vector r. Now, if we consider our definition of the quantity c, the energy, and we compare the energy integral with the Hamiltonian, then it is obvious that the Hamiltonian is the energy integral times the reduced mass. So in this formulation, the Hamiltonian is the sum of the kinetic and potential energy of the system and equals the total energy, which is a constant of the system. In general, any system of equations that can be written in the form where h is a function of q, a generalized coordinate, p, the generalized momentum, and the time, is said to be a Hamiltonian system, and these are Hamilton's equations. At first glance, it may seem perverse to express the equation of motion in this form. However, the properties of such systems make coordinate transformations easier to carry out, and this will be particularly useful when we investigate resonant phenomena. In addition, such transformations may simplify the problem and lead to a solution.